All right, we're here in Raleigh at Schenck Forest. This is NC State's property, managed by the Forestry Department here at NC State. And today we'll look at some soil pits that'll be in the woods, more associated with forest soils and forest productivity. But where we are right now is sort of near the PNC Arena, and this area of North Carolina is our felsic rocks. So this is the Raleigh belt, primarily metamorphic rocks here with igneous intrusions up through, and so you get differential weathering in the soil profiles, especially in residual soils. Very similar to what we have at our Lake Wheeler facility. We have our uplands that are primarily residual soils, moving down to colluvial soils, and then eventually alluvial soils at the bottom of the hill, and they're classic catenas. So today we're going to talk about what distinguishes soils in the woods from soils in the Piedmont and agricultural fields, and we'll talk a little bit about how to identify differential weathering, colluvium, alluvium, focusing in this case here in Schenck Forest. So the first pit is at this landscape position where we're standing right now, which is the roughly summit position, and as we know from extensive talking, we should expect residual soils that are relatively well drained at this landscape position. So we're going to go and start taking a look at these soil pits here in the woods. All right, here's the first soil pit here in Schenck Forest. We're at roughly the summit position. When we're on the summit position, we need to think about residual soils. And as you can see around us, we're surrounded by trees, primarily loblolly pine here, very important for the economy of North Carolina is the growth of loblolly pine. This is your softwood, or if you go to Home Depot, that's yellow wood. So what we could see here, and what we see a lot in our wooded areas, is the soils are pretty beat up in areas that are reforested in North Carolina, especially in the Piedmont. So in the late 1800s, early 1900s, there was cotton, tobacco agriculture across the Piedmont with no BMPs, and what happened is you lost your fertility. So your AP horizon or A horizon eroded from these positions and went down the hill into the bottomlands. And consequently, because of that, we have very little humus in these soils, especially in the upper mineral horizons, the A horizons. And you can see that here. We have a very thin zone of A horizon, maybe an inch thick. Because this has reforested and we have pine, and pine litter is very acidic, it's very problematic for microbes to break down relative to hardwoods. What we're forming here at the very surface is an O horizon. So we have about an inch of O horizon and then maybe an inch of A horizon here. This obviously is eroded. It would have been plowed in the past and it would have had an AP, but where did all that material go? It actually went down the hill. And we'll talk about that a little later. So this is very light and fluffy material, the O horizon. We can spread it out, but you can see in here we have roots, and we have a lot of pine needles that are intermediately decomposed or even well decomposed in this situation. So we'd have to look at rub fiber content. This is either an OA or an OE horizon. It'll probably come out OE, which is typical of our forest O horizons. So that's the first thing off the bat you need to think about. In forests in North Carolina, Piedmont, these were fields at one point, but the areas that were reforested, especially a long time ago, were the worst productive lands, and so they were abandoned first. Pines do pretty well on a site like this. We have low nutrients, relatively low water holding capacity. We have a lot of issues here. These pines have tap roots, and so they can anchor themselves in pretty well, access water, and they don't need a lot of nutrients, especially base cations. So this is a felsic crystalline soil. There's a lot of iron oxides, as you can see. And the interesting thing about, not only do we have erosion, but you can see in the pit here on either side of the tape we have different characteristics. And this is very similar to what we saw at Lake Wheeler. What we have here is resistant felsic rocks, likely igneous intrusion on the right side here. And that is intruded up through the country rock, which was a more weatherable country rock, which would have been likely a gneiss or a schist here, but it would have had more base cations and therefore created more clays and created more secondary iron oxides, especially biotite, mica. The black micas have a lot of iron in the crystalline structure. And so what you're seeing here is likely two different rock types. This is the metamorphic rock. This is the igneous rock that came up through the metamorphic rock, and because of that we have differential weathering and differential erosion that's occurring on the landscape. We have different properties right in this soil pit here. So we're going to zoom in a little bit here and talk about the subsoil characteristics here in a second. So we're going to look at our subsoil characteristics, our diagnostic features for classification here. Because these are felsic rocks, they're very low in base cations. We tend to have very low base saturation at depth, and because these are very old weathered soils from residuum on this landscape position, we tend to have very inactive clays, one-to-one kaolinitic clays that dominate. So these tend to be kaolinitic soils, and because of that we get, instead of argillics, we get candic diagnostic horizons because the apparent CEC is very low. And if you get candic horizons in a situation like this, typically when we're mapping, we'll map a soil with a deep BT or candic. We'll map, say, this side as something mapped typically at a series level as Cecil, which is the state soil of North Carolina. And then if you see morphology like this, where it's much shallower to the sea horizon or the saprolite, which is here, easily dug, highly geochemically weathered sea horizon, which is our saprolite. Because it's shallow to saprolite, the soil over here would classify at a series level as pacholite. So you'll see in soil maps around Raleigh in North Carolina, it's Cecil on top of the landscape mapped, typically at the summit and shoulder positions. And then as you move down the steeper back slopes where you have more erosion, you'll have mapped pacholite. They exist on the landscape intermingled. The only difference is they both have candic horizons, they're both can haplodults, but this one is much shallower to the sea horizon than the Cecil. Some distinguishing characteristics. We can tell that this is a very stable and old soil. We go from sandy loams typically with less than 20% clay at the surface in these soil pits to 40, 45, 50% clay in these particular soil pits. And that clay is fairly evident on the PEDs or subangular blocks here. This is from the BT horizon. You can see this is sort of the matrix color, is sort of this yellowish red color, and then you'll see these waxy coatings on the outside of the PEDs or the structural shapes. Those are your clay foams. And this is why when we do color in the subsoil, we'll do a broken PED and try to get to the interior and see the interior color. There are many different colors here. There are a lot of clay foams. This is textural class of clay. I believe it's about 45% clay. So you go from 15 to 45% clay, a large increase through the process of eluviation, and eluviation called lessivage, or the movement of clay. So that's what we have. Very nice distinct clay films here in our candic. And then over here, looking at the pit on the right side, we have our sea horizon. So they're geochemically weathered, altered rock. You see the original structure of the rock, foliations, still intact. The yellowish color gives it away. It's much different color than the argillic or candic, which is red, but it's saprolite. It's a sea horizon, so I can crush all this up very easily. Highly weathered. So what you're seeing on the right side is predominantly saprolite or sea horizon, but there are zones in here where it's consolidated still. Not too consolidated, so here's my knife. And I can cut right through that material. And so we'd probably call, depending on where you are in here, BCT. Sometimes people will call this like a CRT. So we're just calling the morphology that we see. The T is indicating clay movement. This clay is definitely not formed in place. It's coating around the immobile or non-moving quartz fragment, and it's being coated from above by clay over time. This is a really nice example of differential weathering within a soil profile. Highly weathered intermediately weathered, and then even the least weathered over here, and that's all related to the amount of silicon you have, the amount of quartz you have. So really high in quartz here, likely an igneous intrusion if you really look hard, and I'll post a picture of this. These zones of felsic material are in distinct bands, so it's highly indicative of an intrusion of igneous material. So just some more things to think about in the Piedmont. If it's mapped Cecil or Pacolet, recognize the two are nearly indistinguishable on the landscape. They undulate up and down, and the only difference between those two series is the depth of the sea horizon. So we're gonna take a quick, so this was mapped to Cecil, but we got Pacolet and Cecil. We're gonna move down the hill a little bit to the steeper back slope and take a look how the properties of the soil is changing with elevation. All right, so we've moved down the landscape from the summit position where we just were. The summit position was mapped to Cecil, but we got a little surprise with some Pacolet in there. Not uncommon in the residual soils of the Piedmont to have undulating sea horizons or even rock coming up towards the surface because of differential weathering. Here we're on a back slope, so we're on the lower back slope. We've moved 50 to 100 yards away down the slope, and you can see on the surface the orientation. The slope is generally moving off in this direction towards floodplain down below us. Something you can see pretty evidently, even say on this side of the pit, is the upper material has a high percentage of angular coarse fragments. And there's two reasons for this at this landscape position in the Piedmont. One, these are resistant, so you can see it's primarily quartz. So this is our most resistant fraction. But because of erosion in the past on slopes like this, at about a 10% slope, you're losing all the fines down the hill, leaving behind the coarse fragments. So the upper horizons tend to be very high in coarse fragments in landscape positions like this. And the other thing you can see in the pit face over here is these coarse fragments are randomly oriented. So this one's oriented like this one's oriented straight up and down, this one's oriented like this. And so there's a random orientation to the coarse fragments. And when we see random orientation of resistant coarse fragments, we usually think colluvial. And so what happens on these back slope positions is it's a transition between the residual soils, which are predominantly up the slope, and the colluvial soils, which are predominantly down the slope. So here at these landscape positions in the Piedmont, you tend to get a thin cap of colluvium over top of the residual. And so we're gonna take a deep dive, or a more deep dive, into this soil. But the first thing you can see off the bat is we're in the woods again, loblolly pine. Here's our coarse fragments, and then the coarse fragments with random orientation start to go away with depth. The uppermost horizons here are colluvial horizons, but notice we have humus incorporated down below 20 centimeters at this particular landscape position. The one up the hill barely had 5 centimeters of A horizon. So here we have A horizon that extends almost to 30 centimeters. So what this is telling us is that this was likely plowed in the past. Notice how this brown color is very light. That's from plowing, incorporating the organic rich O horizons and A horizons with the underlying subsoil, and it comes out a lighter color. So this soil shows that past agriculture did occur here. And then you notice the subsoil really starts getting more red, but there's a transitional zone right in here which is pretty yellow in color. And if you look across the face and this horizon below the APs, and actually here I'd call 2 APs. You call like a darker colored AP and then a lighter colored AP, so AP1, AP2. Then there's a horizon right here. It's kind of a transitional horizon. It's kind of like the BTs below. It's kind of like in a situation like this, it's kind of like an E horizon. So something that's this light colored and low in clay, we call like a transitional BE. It's kind of like an E horizon from eluviation of clay, but not quite to the colors that we'd like to see for a straight E. And it's kind of like the B down below. It's got structure, it's got color change, etc. So this is a classic example in this lighter zone right in here, where we call a BE. And if you look around in the BE, there's significantly less clay. So this jumps from something like 20% clay to in the 50s down here. There's random oriented quartz fragments in this as well as the material above. So the first three horizons, AP1, AP2, BE, are in colluvium. As you drop down, clay really picks up to about 55% here, and you can see clay films. We have moderate subangular blocky structure, our usual structure around here in our BTs. This is a Schenck horizon. This would classify at a series level as the Cecil Soil series. But you can see, even without wetting that material, how shiny it is. There's a lot of clay in here. So we're at 52% clay in the BTs. The random oriented rocks at the surface go away as you get into the BTs. And so what this is indicating to me is that we have lithologic discontinuity. So the first three horizons are formed in colluvium. The bottom two horizons are formed in residual materials. So we have a 2 BT here. And the pit's kind of sloughed in a little bit over time. But as you get deeper in the profile, here the clay really goes away and the primary minerals really start picking up. You start seeing all these flecks of micas, and it has slumped in a little bit. Ideally we'd be down like another half a foot and you'd see it more clearly, but we have a transitional BCT here at the bottom of this soil pit, and the C horizon, the saprolite, is not too far below. So here we have a lithologic discontinuity, which is very common at this landscape position, middle to lower back slope. We'll have thin colluvium over residuum. Random oriented quartz fragments are the keys. This site's been eroded. It's been plowed in the past, even though it's been in forestry probably for 50 to 80 years. And then a nice Schenck horizon underneath. And if we're mapping this, we'd map this as the Cecil Soil series. And so mapping is a little tricky in areas like this because you intermix Cecil and Pacolette. They're very similar in interpretations. So we draw a map unit, would say predominantly it's Cecil, but we'd have some percentage that would be Pacolette as well. Typically something like 10 or 15% Pacolette within, as inclusions within our units that are Cecil around here. This is the state soil again of North Carolina. The state soil of North Carolina is all around Raleigh. It's in the woods, it's in the farm fields, it's everywhere. It's a really red altisol with low 1-to-1 activity clays, kaolinitic. So that's the back slope position. We're going to take a little walk even further to the land of colluvium, down the slope to the foot slope position where All right, we've moved down the hill from the back slope position where we had a little thin cap of eroded colluvium over top of residual materials. Now we're in the bottomlands of the Piedmont. We're at the foot slope position. You can kind of see in the pit face here, it's this concave shape. And up the hill is over here where we just came from on the back slope. And then there's a floodplain over here to the lower part of the landscape. So we're in that transition zone between the upland and the floodplain. And you get some really weird transitional soils at this landscape position. Now, usually when we think about foot slope, we think about colluvium, thick colluvial materials. And we do have colluvium here, but it's not as thick as you would think because we're kind of out on the edge of the foot slope. If we went up the hill a little bit, we'd have a lot more colluvium. But what you can see here, it's not too distinct, and we don't have much light today, but You definitely see a lighter color up here, a lighter orange. When I poke the material on top, it's pretty sandy, it's pretty loamy. When you run it in the lab, it comes out fine sandy loam. So we have an A horizon, and then if you take this material out, underneath the A, it breaks into nice, weak subangular blocky structure. No clay films, not a lot of clay alluviation. The upper 30 centimeters is very loamy. It's very fine sand. So can't ribbon it too far, but we can ribbon it. It's fine sandy loam. So here we have an A, and because we have a subangular blocks and we have our orangish colors, iron oxides, it's a weakly developed B horizon. So we have an A and a BW that's formed on the surface here. As we get down to about 30 centimeters, it's not massively obvious here because notice the color of the soil is pretty brown. So we don't have a water table here. As we'll look at the stream behind us in a little bit, the stream is down cut to such a level that it's lowered the groundwater table. And so the groundwater table is nowhere to be seen at this foot slope position. And because there's no water table to preserve relic features or old features, we have an old soil here that's buried under thin colluvium, but the old A horizon, which is right in here around 30 centimeters, is highly oxidized. So there's a lot of oxygen in here. The microbes, it's nice and warm. There's nothing really impeding the microbes here. And that old A horizon, all the organics that are easily broken down and turned into carbon dioxide are being done just that. This material on top is probably 200 years old. It's from agriculture that occurred in the past up the hill. And over that 200 years of burial, the old A horizon is not receiving any inputs from leaf litter, therefore it's not accumulating new humus, but the microbes can still do work, and what you're having is a net depletion of carbon here. This is very common in non-wetlands to see buried A horizons that are really depleted in carbon. We can tell it's an A horizon. It's got a darker color. It's got subangular blocky structure again. And if you look around in here, you will find charcoal, little bits of charcoal here and there. This is likely the pre-colonial surface. But you can see it when I pull it out. It is distinctly more brown than the material that's burying it. So here's the upper BW, here's the buried A. And we also have a lithologic discontinuity at this point. So the upper material is slope wash. It's sometimes called local alluvium, sometimes just called colluvium. It's all sort of rainwater and gravity just driving material down, fine material on top. So we have slope wash, local alluvium, colluvium, whatever you want to call it, on top. And then below that, because we're close to the floodplain, we have rounded coarse fragments. We're going to talk about the subsoil here in a second, but this is a buried alluvial soil on a high landscape here. All right, so how do I know that I have a lithologic discontinuity from alluvium or local alluvium that came down the hill versus the underlying material? Well, the first thing is landscape position. We're fairly close to a stream, which we're going to walk down to in the next soil pit down the hill. We have a color change. Obviously here we have charcoal, we have subangular blocky structure indicating it's a previously stable surface. And as we get into the subsoil below 40 centimeters, every once in a while this is fine alluvium. It's been moved by water. And the big thing you want to do, and we've talked about alluvium before, is look for coarse fragments. And when you find coarse fragments that are well rounded like this one, there's definitely water movement that's occurred and abrasion has occurred and rounded this fragment. So every once in a while you'll find a little coarse fragment, a little gravel in here, and they're well rounded. So you know that this material on the bottom is transported a fair distance by water. So what we have here is basically colluvium on the foot slope position, which is anthropogenic, over a previously stable alluvium. And this we would call old alluvium. And there's a distinction between recent and old alluvium that we make. The recent alluvium is alluvium that's most likely associated with current flooding and floodplain dynamics. Old alluvium is reserved for terraces, which are remnant floodplains. They're ancient floodplains. And how do we we tell the difference between old alluvium and modern alluvium. Landscape position plays a lot. The further away from the active channel you are and the higher up you are within the floodplain system, typically you're talking an old terrace situation that's been downcut and abandoned by the stream system. And what happens, because these terraces are much older, they're older surfaces of alluvium, they tend to be way more pedogenically developed in the subsoil compared to more recent alluvium. So more recent alluvium in the Piedmont tends to form young soils, entosols and inceptisols. Terraces tend to be altisols and alphasols. And so you've had tens of thousands of years of this alluvium sitting on the landscape, not being disturbed by current flood dynamics. And what you get is an uptick in clay. So we go from loamy material on top here. We have fine sandy loam, then we go to sandy clay loam in the buried A, and then we go up to clay loam as we move down into the subsoil. And you see again nice subangular blocks, but if you look closely here, you will see clay films. They're not as pronounced as in the upland, but there are faint clay films. Here's one right in here. It's these waxy coatings on the outside of the PEDs, and there's faint clay films all through here. The clay ticks up, keeps going up, and is up into clay loam by the time you get to the bottom. You see the shininess here. And so our clay content goes from less than 20 to like 35% with depth here. And so because we have faint clay films, we have a big uptick in clay going down in depth. This is a mantled altisol. This is a terrace soil. So this is an old floodplain. It's alluvium, but it's old alluvium. And this is a mantle. So in class, we're going to be talking a lot about buried soil rules. Remember, the magical number is 50 centimeters. You need 50 centimeters of new material on top. If you don't have 50 centimeters, so here our old soil starts at about 30. This is considered a mantle. So this soil we would classify, we would ignore the mantle for classification. It would start at the buried A. So we have two parent materials. So we have here we'll have an A, a BW, a 2AB, it's a buried A horizon, then a 2BTB, 1, and the 2BTB, 2. For classification purposes, we're going to ignore the BW mantle, and we're going to classify the lower material because of the base saturation here being low. This is an altisol. So remember, buried soil rules are very important anytime you have human transported materials, and especially as you get low on the landscape and you have colluvium or alluvium burying previous surfaces. Recognize where you have to start the classification. So this is a pretty neat soil. It's an anthropogenically buried terrace. We're going to move down the hill even further and look at the more recent alluvial soils that form in the Piedmont. Coming to you live next to Wade Avenue over here. This is the main creek at the bottom of this catena sequence. We're working our way down. Very common in Piedmont morphology, but notice how small the channel is relative to how wide the actual channel area is. This stream is slightly underfit, which means when you see this morphology, think massive storm flow. So we're right near downtown Raleigh, PNC Arena, everything drains into this area during really high rainfall events because of the impervious surface. This whole riparian area is going to fill with water. So you tend to see these small streams in these large corridors. Think storm flow, especially in urban areas. And because with that storm flow comes extreme energy, that is just all these semi-rounded coarse fragments and coarse sand in here. So this is all the material that can't wash out. It's very high energy. This is what we call the bed load. It kind of rolls every time it floods in here. Then it might roll just a little distance and then it'll rest. And then it'll flood and it'll roll and it'll rest. So what you're seeing is what we call the bed load. So we don't really map soils or think about soils here within the channel. Where our soil system does start is right adjacent to the stream channel, and this is the highest energy place in the entire floodplain. It's typically a landscape we call the natural levee. It's where you get the turbid flow goes up over the natural levee and immediately drops the coarsest materials, because the stream energy dissipates very quickly when it hits these trees. The energy slows down, the speed, velocity slows down, and initiates dropout. So the sand will drop out first on the floodplain. And if you want to find an entisol in the Piedmont around Raleigh, this is pretty much the best place to find an entisol besides one that formed in human transported materials. So we're going to look right over here at the natural levee. Follow me. An artifact from the past. Bud Light in an aluminum can. This is buried in the soil. We put a U on it. Human manufactured materials or artifacts. Beautiful. All right. The first step out of the channel. The channel ends about here. The first step, it tends to go up in elevation very rapidly. And this is where your sands drop out of suspension. So this, I can make a ball, I can toss it lightly, but notice it's falling apart. And when I try to ribbon it, no luck. Can't ribbon this material. So I can make a ball or a cast, I can toss it lightly, but it starts falling apart. But I can't ribbon it. This is loamy sands. This whole area from the base of the current channel, which is right about there to the top of this natural levee, is all loamy sands. Because it's all loamy sands that are structurally massive, you basically have an A horizon over C horizons, no diagnostics, you get an entisol. But if you want to step up here, you'll see the area encompassed by the entisol is not very big, so we can't really map it. So here we are, I'm standing on top of the natural levee right now, and this entisol is all this sand that is deposited, but notice it comes up, and the landscape dips down, and then by the time you're at the line here where the trees start again, that's an inceptisol. So literally we have like 20 meters at most of entisol. We have a very small area spatially of an entisol, and then we're right into inceptisols almost immediately. If you want to find an entisol, you're never going to find them really mapped exclusively in the Piedmont. Some areas you'll find entisols mapped if it's in an upland, or once in a while we have a larger river system, you'll have a larger natural levee, but this is very common in small streams of the Piedmont. Very narrow strip of entisols going into inceptisols as you move back onto the floodplain. So we're going to move ahead and check out a soil pit further back away from the stream here. All right, we're here in the rain. Got the GoPro running. Beats being in the office. So here's our pit. Classic soil series mapped Piedmont and the coastal plain of North Carolina is the Chewacla soil series. It's the garbage can. It's any flooded soil. It's an inceptisol. It's a fluviquentic distrodep. So we're on the floodplain, kind of in the middle position. We're between the foot slope, which is upslope here, and the natural levee, which is downslope, where the active channel is. And we're kind of at that sweet spot where we get our classic inceptisols to form in the Piedmont. Now, we talked about alluvial soils and what makes them unique, and you can see right off the bat, we have a buried horizon here. We have a buried surface. Very common in Piedmont to see buried surfaces. The material on top is 200-300 years old. It's anthropogenically generated from the upland. The material on the bottom is older alluvium, but it's not as old as at the foot slope position where we had an ancient terrace. We don't have any evidence here of clay alluviation. So let's talk a little bit about distinguishing features of this soil. We have an A. This is all an alluvium. The upper material is much younger than the older material. Talked about it on the alluvial soils section. Some people call lithologic discontinuities here, others will not. We have an A. Then we move down here, we have a BW. Notice the color, very red in color. The alluvium that was generated during past agricultural activities in this area was very red. Why? Because the uplands, as we saw in our upland videos just today, were very red, in the subsoil especially. What this is reflecting is the uplands have very red soils. Those red soils eroded. That material was deposited here as a deposited material, and it imparted and kept that red color. If this site was really wet, this red color would turn yellow and it might turn gray. But because it's still red, it's indicating that the water table is pretty deep. So we just looked at the channel. The channel was highly incised because of flashy hydrology and impervious surface in this basin. The water table has been dropped, again, anthropogenically because of downcutting. That's resulting from all that stormwater being generated in the basin. And as a result, the channel has cut down and the water table has dropped to meet the channel. And so what we have here is highly oxidized material that's relatively unaltered since it's been deposited 100, 200 years ago. We have an A and a BW, and then we go into our buried soil, which is alluvium as well. I would probably just lean to the side of calling this an AB. It's a buried A horizon. You can see much darker in color here. See lots of bits of charcoal in there. Classic buried A horizon. This is the pre-colonial surface. And then below that, it really depends if you put a 2 or not, but we got a BW here. We wouldn't put a prime on it because it's buried. It's a buried genetic horizon. We have a BW here and a BW here, but because we have the B, it's a BWB, we don't need a prime. So remember, we use the prime symbol on the master horizon only when we have exactly the same morphology. Both capital letters, lowercase letters, and lithology has to be similar to use primes. Because we have that B on this down here, we don't use a prime. So it's A, BW, AB, BWB1, and then BWB2 is at the bottom of this soil pit. And you can see kind of from a distance, we're starting to get gray colors. We're also starting to get black and red colors. So it's a BWB2. We got nice subangular blocks here. But notice we have black colors, that's manganese concentrations. We have sort of these red concentrations of iron, and then notice the gray. So we have zones of depletion or iron depletion. Our seasonal high water table is coming in a little bit before 80 centimeters. So that would make this a moderately well-drained soil. So Chihuahua is supposed to be somewhat poorly drained. If it was somewhat poorly drained, I would expect the redox features to be 50 centimeters or closer to the soil surface. The formative element is fluviquentic or fluventic, depending on what the drainage class is. What that means is an irregular decrease in carbon, Holocene age, which is 10,000 years, with depth. We have very high carbon in the A, we have low carbon in the BW, and then the carbon goes way back up in the buried A. So if you were to look at this on a graph, it would be high, low again. That is the definition of irregular decrease of carbon with depth. This will meet, for classification purpose, the fluve elements. What that means is you have water coming in through the process of alluviation with an A, and alluviation drops new material on top of old material. That old material maintains the carbon. So these soils tend to have very high carbon pools when added to the surface because you have not just one A horizon like an upland, but you have two. So we have very high carbon storage potential here. And this is very classic legacy, sometimes called legacy sediments. These sediments on top were generated as a legacy of past agriculture, no BMPs. And this is the morphology we get and changes in ecosystem services. So this is our catena sequence through the woods. We have our nice Alta soils, then we have our transitional, colluvial, foot slope, weird soils that don't meet many definitions. As we move out towards the stream, we have inceptisols and possibly entasols. This pattern is repeated over and over and over again. Notice that this soil is the only one we saw redox depletions anywhere near the surface. So typically drier soils in the Piedmont uplands, wetter soils in the lowlands. This is how we map, this is our landscape framework, and this is how we draw units on the landscape. That's it for today. Tune in next week for some more information on soils.